Yoon, and I'm a PhD student at Purdue University. So today I'm going to talk about our prototype TRing. And this work has been done with my colleague Yunbo and my advisor Professor Karthik Ramani. So the rise of do-it-yourself and maker movements have resulted in widespread use of additive manufacturing. And moreover, low-cost embedded electronic components like microcontrollers and sensors have enabled the rapid prototyping of interactive objects. However, existing method of making interactive objects still requires the installation of a hardware, including wires, batteries, and ICs to the object side. And this kind of setup requires a battery management for each different interactive object for the use of for the duration of usage. So here we want to propose a potential solution where we reduce the hardware requirements by simply embed a small magnet along with using a finger-on device. So with our approach, we believe that we can support the growing number of novice makers who possess little background knowledge in the electronic components and the sensors. So recent approach have focused on minimizing the post-process of embedding interactive elements to the fabricated object, either using the sensing techniques or printing method. And researchers also utilize the affordance and the availability of everyday object to perform the various interactions. And by utilizing everyday object, the object itself becomes an interface and controller. So in our work, we want to achieve the same functionality with a simple step where we just simply embed a small magnet instead of installing the full hardwares. And finger wearables have been suggested to provide precise and rich interactions. But in previous work did not fully focus on interacting with the object and did not showcase the flexibility in customization. So in our work, we provide interaction with the different object by defining a coordinate system around the embedded magnet, and we also provide a toolkit for the full customization. In terms of the sensing technique, magnetic sensing has been populated to overcome the limitation from the vision-based approach. So we further improved the existing magnetic sensing method where we adopt a particle filter to enable the finger tracking around the magnet. So how do we make object interactive with a seamless manner? So to do this, we need to improve the accessibility of making object interactive. So here are 4 things that can improve this. So first is to minimize hardware installation and low cost for implementation in terms of time and the monetary value, and supporting high flexibility in customization, and lastly, guarantees the instant control accessibility upon implementation. So to this extent, we suggest following workflow. So first, with a given toolkit, user customize the interface. And with this toolkit, users can customize various interface elements and map different functions. And by embedding a small magnet to the object in a guided position, users can embed interactivity to the different objects. And lastly, user interact with the object by simply double tapping on the different object to recognize different object ID and perform various interactions. So in order to achieve this workflow, following requirements should be met for the sensing technique. First, it should support the various interaction techniques, including discrete and continuous interactions. And second, no user-based calibration or training should be required. And lastly, it should be less obtrusive to both users as well as objects. So here we present TRing, which is a finger-on device with the magnetic sensing technique, which provides the fingertip tracking around the embedded magnet. So by embedding a magnet in the object side, we bring interactivity to object without installing any hardware inside the object. So here it shows the prototype of our device, and here we employ 9 degrees of freedom IMU to compute the 3D position from the magnet to the fingertip. We also provide a magnet holder for easy attachment of the magnet to the existing object. So from here, I'm going to explain about the principle of our sensing technique. So to to implement the magnetic tracking around the permanent magnet, we need to solve two requirements. First one is the orientation of the fingertip near the magnet and the initial orientation of embedded magnet. To solve the first part, estimating orientation near the magnet was hard to achieve because of the magnetic distortion. And here we approach with two key solutions. So first, we use change of magnetic dip angles to detect the magnetic distortion status. So this enables fast magnetic distortion detection, comparing the normal magnetometer values. Then we employ a particle filter to estimate the orientations. So we initiate the particle filter only when there is a magnetic distortion, and we update the weights of the particles using an axis of ellipsoid of direct cosine matrix. So this tells how much we are off from the clean magnetic field. And we keep iterating the particle filters when there is a magnetic distortion. So here is a short demo video on the comparing between existing method and our method. As you can see, with the previous method, it's hard to estimate the orientation near the magnet. But with the particle filter in it, we can robustly estimate the orientations. So using this estimated orientation, we can actually do the position tracking. So position tracking is based on the general magnetism theory. And to remove the bias of the initial magnet orientation, we always set magnet's north pole facing upward when it is installed in the reference object. So with known orientation of magnet and the fingertip, we can calculate the relative distance between the magnet and the fingertip based on the magnetic field vector readings. So this video shows the real-time position tracking of the fingertip, and the black dot indicates where the embedded magnet is. So how do we configure the location of the embedded magnet? So we provide the proof of concept toolkit where it demonstrates the location of the embedded magnet. So here users can customize interface elements, and our algorithm computes the optimal location to embed the magnet. And after 3D printing, it becomes an interactive object. So here's a short demo on how users can use our toolkit. So users can simply drag and drop the interface elements. And after the computation, it finds the location of the magnet, location of the embedded magnet. And this can be exported to the 3D modeling tool for the 3D printing. So what kinds of interaction are supported using our prototype? So with our prototype, we support both discrete and continuous inputs. So discrete inputs are event-driven approach, including button, gesture, tilt, and proximity, and these are based on the threshold values. And continuous inputs utilize ongoing tracking, such as tracing, linear slider, and rotary slider. And we combine fingertip tracking with the motion events to form a complete input. So, for example, the motion events include the surface tap or the finger lift. So before going for the example application, here we just summarize the experimental and user study results. So initially, we performed several experiments to check the accuracy of our sensing technique. And as you can see from the graph, previous method shows the high errors under the magnetic distortions. So with the particle filter in it, we reduced the max error from 100 degrees to 15 degrees. And this shows the robust estimation is enabled by the particle filter. And with the motion capture camera, we collected 30,000 data points to compare the absolute position tracking accuracy. So with a confined volume of 120 millimeter by 120 millimeter by 100 millimeter, we achieved the distance error of 8.6 millimeter. And if we narrow it down to the 2D tracking, it shows the errors of 4.4 millimeter. And we also noticed that our prototype works better with the relative position tracking. And when we only compare the deltas between each data point, the error became under 3 millimeter. And this implies that the prototype suits for a cursor control task. And we also tested targeting accuracy in 2D plane, since this can reveal the proper interface element size that we can adopt in the system. And here we simulate our possible entering direction, including, so we brought the prototype from left, down, up, and top. Yeah. And with total of 43,000 data points, the average targeting error came out to be 4.96 millimeters. So to further verify the feasibility of our prototype for controlling basic user interface, we conducted 2 user study with 12 participants. First, we checked whether the targeting accuracy is consistent across the different user behaviors, including approaching speed, approaching orientation, and the finger positions. And this test aims to verify the accuracy of absolute targeting as well as the targeting through double tapping. And we chose a grid size of 15 by 15 millimeter, which is the average size of a keycap. And as seen from the result, the errors increased with the distance. This is expected because of the degradation of the tracking performance over the distance. And we noticed that double tap shows the higher errors. This indicates that we have to use the double tap gesture within the more confined space. So overall, within 45 millimeter distance, overall accuracy came out to be around about 90%. In subsequent tasks, we evaluated users performing an absolute error cursor control task with a different distance, different commitment methods on different target sizes. So 2 commitment methods used were, first one is the physical tapping on the surface, and second one is a bimanual touch input with a given tablet. And throughout the study, we explored the effect of the different distance and commitment methods on accuracy and reaction time. And from the result, both errors and the completion time were significantly worse in the smallest target size, which is 3 millimeter. And this indicates that the target size of our interface element should be bigger than 5 millimeter for robust performance. And we also observed the different performance between 2 commitment methods. And this tells that the current commitment method should be further improved to guarantee more robust performance. So I'm going to showcase various example applications that shows the capability of TRing. So this example demonstrates a simple process to bring interactivity to 3D printed object. Here, users insert a magnet to build a music box with the various controls, including buttons, and linear sliders, and rotary sliders. And combining 3D fingertip tracking with commitment methods such as surface tapping and finger lift, users can operate all different types of input controls. And this showcases the potential to improve the rapid prototyping process of making interactive objects. And in second example, we implement a TV remote controller in existing furniture by attaching a magnet on the handlebar. So we implement general functions provided in existing remote controllers, like changing channels or controlling different volumes. And furthermore, we also added a finger posture control, which launches the different gallery mode by tilting a finger. And this example showcases the simple approach, making existing object as an instant interface. So to make a change in the interface, previous approach requires the full hardware rearrangement. So in this video, we show how it is easy to change the interface using our system. So we only require 2 steps: replace the interface cover and just update the local coordinate of new interface elements. And as you are aware, the magnet is inserted under the bottom of the desk, and we just place the interface cover in the same locations. And this example illustrates the high flexibility in customizing interface using the prototype. And the high durability of magnets against heat and water makes a good fit to be used with the clothing. So we demonstrate controlling a mobile device using a magnet embedded inside the jacket. So this illustrates the potential of our prototype to be used as a wearable input. So I'll conclude my talk with the limitations and the future works. So our tracking, as you're aware, our tracking exploits the magnetic sensing. So this indicates that our prototype will not work robustly with the ferromagnetic materials. And in terms of the scalability, currently our prototype supports the region of 120 millimeter by 120 millimeter. Although this is good enough for the small object, it is not sufficient for a big object like a big table. So currently we are in the process of obtaining the embedded magnet's orientation by using multiple magnetometers. In this way, we can embed multiple magnets on a big object like a table to increase the physical volumes for interactions. And lastly, we only explore the physical tapping and finger lift for the commitment method. And from our user study result and feedback from the users, we received lots of suggestions on using body of the prototype as an interaction medium for commitment. So it is in our interest to develop a commitment method using a body of the prototype, such as embedding a capacitive sensor to the body of the ring. Yeah, thanks for listening, and I would like to answer any questions.
Questions, please? Far back right there.
Zhang from Tsinghua University. So, TRing use magnetic sensing, and it should require a magnetic clean environment. So there's a clean area around your device, and I'm just curious, how large is that?
Yeah, so as mentioned, the limitation is not going to work robustly with the ferromagnetic materials. So in our example, we try to show our example with a 3D printed object and everyday object which does not have a ferromagnetic materials in it. Yeah, I mean, I think that's the basic limitation for using the magnetic sensing.
So basically, so you didn't explore the possibilities that to interact with the multiple magnets or multiple objects? Or
Excuse me, which magnets?
What? I'm sorry?
Also, what? Yeah, I couldn't hear. Yeah.
So my question is, so did you try to interact with multiple magnets?
Also, so we are currently, so we found out that if you use the multiple magnetometers, there's a potential solution to find the embedded magnet's orientation. But we haven't tested yet, but we are currently working, it's currently work in progress.
Question on the left, yeah.
This is Song-an from UIST, Korea, and my question was probably you may say, but that in haptics that users can use 5 fingers, like for playing, let's say, air piano or air guitar. Is it possible that technology can be extended to multi-finger technology?
So I think, so you're asking about whether the possibility of using multiple magnets or multiple sensors to detect the multiple finger movements.
Yes, then it would generate a lot of applications, industry and academia.
So I think there is a possibility to use substituting the current permanent magnet to the active core magnet, but in that case, it reduces the advantage of current technique where, in that case, although the battery consumption is still low, we need to put the battery in the object side. But with the active core sensing, I think there's a high possibility.
Thank you.
Time for one last quick question. Okay, let's thank our speaker, and let's thank all our speakers.